Hopefully in this video we'll have an understanding after you watch it of what a weighted network is and what a spanning tree is. Okay, so over to my right I have a weighted network. Okay, so it's a network. It looks like other networks we've talked about in previous videos, except where it has numbers on every edge, or link, whatever you want to call it. They call it edge in the book. Usually, they say they're going to call it link, but then they call it edge. So anyway, line, you can just say line, right? Every line has a number associated with it. So this is a network, which remember, a network is just a connected graph. And it's a weighted network because there are numbers associated with each edge. Now these numbers could represent different things. What they actually represent though is just some cost. By cost though, let me write this down. They're associated, probably spelled that wrong. I don't know how to spell the word associated. Numbers are associated with some cost. That might be right. Look that up. The cost could be actually a cost. It could be how much money it takes to go from A to B, or how much maybe a road cost in hundreds of thousands of dollars to be constructed from A to B. But by cost, it could also mean something else. Like it could just mean the mileage between A and B. It could mean how many kilometers are between A and B. But it means something, in other words. It's weighted. The number has a meaning, okay? When we get to specific problems, they'll tell you what the number means, whether it means mileage or how many minutes or whatever it means, but it's some cost. Okay. So if you look, like I said, this is a network. It's weighted because it has numbers associated with each edge. But is it a tree? Think about that for a while I get a drink of Gatorade. I should try to get a sponsorship with Gatorade. I guess I'd have to drink it on camera though. There, send me some money. I know you're not. I only have one subscriber. So, don't forget to subscribe if you like these videos. Also, if you don't like the videos, subscribe. Can't hurt, right? Alright, so, is it a tree? I asked that before and you were supposed to answer it. No, it's not a tree. There are quite a few different circuits here. This is a circuit, K to N to L to K, K to B to C to L to K, J to K to B to A to J. So it's not a tree. That means there's redundancy. Okay? If a network is not a tree, then there's some amount of redundancy. That means, let's say, for example, they're going to talk about it a lot in some of the examples in the book and on PowerPoints. This is a weighted network from the PowerPoint, but I made it smaller. There were more vertices. I didn't need to make it the full size to show what I wanted to show. If this is, for example, pipeline or fiber optic cable or electrical wires, and this weight means how many millions of dollars it costs to lay the wire or cable from A to B. That's $23 million right there. It costs to lay a cable from A to B. Well, if these were actual cities, do you really need all that redundancy? Can't you just make this a tree and get rid of some of the edges? The answer is yes. You might want redundancy for some reason, but if you can save hundreds of millions of dollars, you're going to try to make this into a tree. Okay, so let's come over here and talk about subtrees and spanning trees. Okay, so I'm going to read this definition first, then talk about my picture. This picture is also from the PowerPoint that goes with section 7.2. I want to mention that because I know you know that on the website there are a lot of other features like videos, PowerPoints, applets, and other things like that. But if I don't remind you, you might forget. Okay, so a spanning tree in a network is a subtree of the network that spans all of the vertices. Spanning all of the vertices means that if there's going to be an edge connecting all the vertices together. So if you look at this network here, this is a network because it's connected graph, but it's not a tree because there's circuits. But can I make this into a tree? The answer is yes. You can turn any network that's not a tree into a tree by getting rid of an edge or edges that are redundant. So you notice how there's two edges that come to G. You don't really need both of those edges, and G would still be connected as long as you have one of the edges. You can't get rid of both of these because then G would not be connected anymore. But let's say you could get rid of this. Okay. Okay, you could get rid of that. Let me draw that edge back on there. It still wouldn't be a tree because you'd still have something down here, but I'm going to show you one of the trees that you can get out of this pretty soon. I don't want to erase edges though. I want to just write them in a different color if that works. So notice you could get rid of either that edge or that edge. As long as you still have one edge coming to G. And the same here. Well, this is a little bit different actually. No, it's the same. As long as you have one of these edges coming, as long as you have this one or this one, and actually I think another one can be gotten rid of too. I want to do this in real time. I could have looked at the answer, but I want to do this in real time to show you how to do it. Well, let's look. If you remember the formula for redundancy, it was this. Remember, redundancy means how many edges do you have that you don't really need, and it could still be a circuit, or not a circuit, a network. It would be a tree, actually. So, M is edges, N is vertices. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Hopefully I counted that right. 1, 2, 3, 4, 5, 6, 7, 8. So our redundancy here is 2. Okay. We have 2 extra edges that we don't need. And like I said, you could get rid of this one and this one. Now, it is a tree. Okay? It's a spanning tree because it touches every vertex of the network. Okay? So, is that the only tree that there is? Is that the only spanning tree that there is? No, that's just one of them, right? Let me redraw it again. Like I said, you could have also gotten rid of this And can you get rid of this? Let's see if that works. First you just have to ask, do we have a circuit now? No. Is it a tree? Yes. So this is a spanning tree. So it turns out, I think in this example, let me redraw it again. I'm not going to do every one. I think it turns out in this example, there's actually 11 different ways you could do it. Okay. Well, now imagine if this was a weighted network like this. We're trying to figure out the spanning tree that has the least cost. Okay. So we could do it with that. Matter of fact, I might come back in another video and maybe redraw this bigger. And we're going to see how to make that what's called a minimum spanning tree. It'll be the spanning tree that has the least weight when you actually, first we're going to just talk about making it into a spanning tree. Then we'll worry about whether it's minimum or maximum. But that'll be in either the next video or in 2 videos.